Hi everybody, how are you guys doing? Awesome. So a bit of a fact, so contractor is actually my last name. So it is. yeah, no, I'm just saying it's really hard because there are very few of so no, just no offense, it's just anyways, so thank you all for coming today, and thank you for being here and spending your evening listening to this presentation. I think the reason, one of the things I wanted to put forward while doing this presentation was this is, I want this to be a more, I guess, a feedback gathering session, instead of a more instructive session, because what we have done in the past couple of years to months is we've worked on something that we are actively seeking feedback from the community from. What I'm about to present started as a university project. Actually, it was a course project which turned into a university project, into a research paper, and now there's some active development going on that. And if anything, this instruction is this session is to get some thoughts provoked, get some feedback gathered, so that we can the bigger community can benefit from it. And I'm hoping that at the end of this session, there'll be more interest and more active development and research in this area. So that's where this I'm trying to take this presentation. So having said that, right, the goal of today's talk is to identify. It's to basically talk about a model, about a machine learning system, about an AI, about a program that can actually identify an anomaly in a scene, right? And in this case, our domain is security and surveillance. So like you see is in airports, in bus stations, in terminals, you have always a threat of something being like left alone, and it could be of some potentially dangerous nature, or it could be just somebody forgot something. So and it's in busy scenes and crowded places, even having CCTVs and cameras and state-of-the-art photography, it's very hard to really identify, detect, and actionize against something like that. So there has been some work in this field, but what we believe is, our AI systems, our computer vision systems can do much better, right? Contributing to this area. So that's the goal, to basically build a system, build a model which has enough intelligence that, like a human, if not better than a human, can look at a scene and say that, okay, there's something wrong with it, and then predict what's wrong with it. Having said that, right, let's do a little bit of a pop quiz. So I'll give you the first one, right? So, and the resolution is low, but then again, that's good because that's how a camera sees, these footages anyways. So in this scene, like you can see, there is one abandoned luggage somewhere here, right? So the goal of the program is to figure out where in this scene the abandoned baggage is. So this is pretty obvious. It's doable. I mean, people can figure this out. How about the next one? I mean, can anybody tell me? And this is actually really low res, but can anybody tell me where an abandoned luggage in this scene would be?
In that where the two things come together.
Here?
That one.
Somewhere here. Okay. Any other guesses? Right here?
Yeah, to the right.
Here?
To the right.
Oh, to the right? Here?
No, to the left.
My left. Okay. Somewhere here, right? Somewhere here. Right?
No, to the right. A little bit to the left. There's a stick.
Okay.
That's the one.
Okay, good. Okay. All right, let's see where it is. And again, this is a little bit unclear on this presentation, but this is where it is. Right? So in terms of getting from an easy catch to a little bit harder, now let's see another one, right? Where is the bag here, or the object here? Center top? Right here? Okay. So it's here. Right. So the whole point of this this little pop quiz was I did this. So we did this experiments with kids ranging from 6, 7, 8 years old to adults who've been in and outside of this domain. And what we found out was the average accuracy of the audience that we did this with was somewhere around 45 to 50%. So even for humans, sometimes these scenes, and it looks better on a computer, but in any case, even for humans, sometimes these scenes are very hard to interpret. It's really very subjective, right? For that matter, based on your past experiences, based on things that you've seen and things like that. So, how do you train a program, right? How do you train an AI? How do you train a computer? How do you train an algorithm to detect something like that, right? So that's where this this talk comes in. So let's kind of break down the problem a little bit, right? So if you want to really detect something that's anomalous with the scene, right, or something that's not normal, you have to figure out what that anomaly is. You have to figure out what that error point is, right? So that's the first part in getting to know the system. Then once you figure out what is wrong with the scene, you have to develop a system that can describe the scene, that can tell you, okay, this is what's wrong with that particular object that you've discovered. How do you identify the object of interest? In that case, it was a bag, it was a box, it was a suitcase. But then, is object by itself enough? What do you do with the object? You need to know who was the perpetrator, right? Who was the person responsible to leave that object behind? So identifying the association between the two entities, the object and the person, is very important, so that you can do some actionizing on top of that. And then finally, after having the first three signals, you can classify whether if the scene is a scene with threat, or is it just a normal day, right? And then you go from there. So these are very important things that you need to figure out while looking at some errors in images. So there is some work done here. So there is some prior and parallel work going on in this area. So there have been some rudimentary, I guess, efforts with using simple algorithms like background subtraction. So essentially, you have a background which is with a bag. You have a background which is without a bag. You subtract, find out the difference, apply that model to every new scenery that you encounter. Very slow, very error prone, and every change of a slight variation of that background throws the entire system off. So not very good. There's some other techniques with foreground mask sampling, where you actually take a mask of the foreground and identify the the points of interest. But as soon as the foreground changes, and especially with scenery situations like these, where you have airport terminals where people keep moving in and out, right? Where you have a train station where there's never a single scene, right? It's very hard to statically somehow identify the scene, if you may. There's some recent cutting edge work done by Intel, and actually this is the third link is pretty interesting. I mean, this started sometime when we kicked off the project as well, and then they're doing some good work with CNN. I think, as far as I know, this is probably the most significant or notable CNN-based scene classification, surveillance scene classification work that they have done. So, I mean, if you guys are interested, you should look into these some of these references to see what's going on in this area. Now, what are the challenges, right? Some of the challenges that you faced, and this is not really necessarily related to surveillance. This is actually across the board for just image classification, if you may, right? Like when you want to identify or classify a scene, right? There are viewpoint variations. So you can, I mean, if you mount a camera there, you'll have a different viewpoint. You mount it there, you mount it top down, bottom up. There's just a lot of ways in which you can scale a particular scene. There's also illumination. I mean, sunlight versus like a room light or something. So that makes it harder. There's deformation. That cat looks really scary, but there's deformation, right? I mean, you can have objects in a way that you don't expect them to be. So how do you figure out if that's the object of interest that you want to detect? There's background clutter, where you have an object, but just like we saw in the first scene, we had the bag next to the chair, so you're not sure which one it was. And then obviously variations between classes. So a bag looks differently from a suitcase, looks differently from a box. So there's multiple variations of the same object. So lot of challenges in basically detecting something and having a high probability and confidence of classifying it as an object. So what do you do, right? And then the biggest challenge for us in this particular domain was the availability of the data sets. Now, this surveillance kind of data is not really public. I mean, it's highly sensitive data. It's very closed, and you really have to work with the government and all these people to get access to this data. And then even once you get that, you cannot publish that as part of your training data in your paper, because you're very restricted. Like there are some data sets out there, like St. Petersburg subway data set. There are a few that you can use publicly, but they are also very sparse. So now, I mean, you guys know about CNNs. One thing that makes CNNs really good is that you give more training data, it learns from the features, and it produces better results. But we have kind of an oxymoron here where we want to use CNNs. It's the state-of-the-art algorithms and networks to predict image classification, but the data set doesn't exist. So what do you do? So these are some of the challenges that we were up to when we were trying to go through this this exercise, this project. So yes, CNNs is definitely the way to go. I mean, and I guess show of hands, right? I mean, everybody knows CNNs, I guess, right? I'm assuming just heard of it, or at least used it in some way, shape, or form. So just to give a refresher, right? I mean, the way CNNs work is it's derived over the mathematical convolutional operator. So essentially, you take a sliding window, you basically shift it around an image and do a dot product of that window with the part of the image that you're analyzing, and then pass it through a few hidden layers, and you get some scores of and I'll go a little bit deeper into some of those operations. But essentially, CNNs have been recently very popularized. I believe CS231N was a seminal class. It was Andrew Kaparthi, who is now the director of AI at Tesla. He started that class, and it's been I mean, from that paper that he published, it's been really very popular after that. So yeah, some of the basic concepts, right? And this is some of the things I'll be using throughout the talk, so that we know why these are important. So again, convolution, right? Convolution is nothing but an operation where you slide a window of you select, right, 2 by 2, 3 by 3, what have you, over an image, and basically summarize the image into smaller units, and you kind of find these are some of the things that actually also help address the challenges that we talked about before, scale invariance, or viewpoint variation and things like that. Because once you summarize the image into its pixels, you can know that the higher level variations don't matter. And then there is some non-linearity in a CNN. So basically, it's kind of like activation functions. So every time you want to, so the way CNNs works is you do a forward pass of the image where you actually have convolutions over the image, and then you do a backward pass, which is basically calculate the gradient of the image, right, with respect to the input image. And that's how you calculate the loss on a CNN. You know that this is how the classification is better and better over time. And there is something called pooling, right? And pooling is nothing but you take a bunch of pixels, and then if it's a max pool, you take the max on the bunch of the pixels. If it's an average pool, you take an average. That's very important, because what happens with CNNs, especially with images, you have very high resolution images. So if you're talking about basically, let's say 240 by 240 image, right, the smallest size. Now you're talking about that multiplied by 240 multiplied by 240 number of pixels that you have to process, right? So if you take that through multiple layers of a CNN, it really becomes hard. So what pooling does, it kind of summarizes the information in that image, so, and then provides a better computational, I guess, efficiency. And that's basically the output of these three layers is finally plus to a classification layer, which you apply like a softmax to. So as you can see, right, I mean, this is how convolutions work. You have a window that just goes through the image and provides a smaller input. You have a non-linearity function. In this case, it's a max function. So sometimes what we do is, if the input image is it has all negative values, you drop the negative value, put a 0 there, so the gradient backflow is easy. Pooling is essentially, like I was explaining, it summarizes the pixels into so like 16 by 16 grid can be represented in some way, to a 2 by 2 grid, or a 4 by 4 grid can be represented in a 2 by 2 grid. There's interesting thing about pooling is, there was a recent paper by Jeffrey Hinton about capsule networks. Not sure how many of you read that, right? So it was interesting, and we'll talk about this a little later, but he had some strong opinions on why this is not really good, and how this loses information in a CNN network. And then essentially, this should be a very familiar the equation, right? This is softmax. So essentially, once you have the fully connected layers, you apply a kind of like a softmax classifier, so you can convert the scores of the layer into some probability between 0 and 1, so you know which class it belongs to. So having said that, right? So these are some of the data sets we used. So eyelids is a pretty famous data set. It's been used for close to 10 years now. There's a competition that happens every year where you can actually take this data set and try to predict the abandoned baggages, and you can there's a leaderboard there. It's kind of like Imagenet image classification, but only for surveillance. There is Caviar. This is another, it's context aware AI retrieval system something, but the whole point of this data set was to augment eyelids, but this is a more complex data set where you have very busy corridors, the camera angles are pretty skewed up, and that's intentional because then you're now pushing your algorithms to be more and more domain, I guess scene agnostic. There is MS COCO we used, and MS COCO is nothing but an object annotation data set. So basically it gives you like 80 classes of objects, and each of that class is annotated with captions. So it says a man is riding on a skateboard, playing a drum or something. And along with the captions, it also gives you like region proposals. So it basically, like you've seen those bounding boxes, it actually gives you bounding boxes around images. So you can actually say, if this is a busy scene, this is a cat, there's a dog here, and there's a person standing next to them. So it's a pretty interesting data set. They actually released a new one just a couple of weeks back. So if anybody's into object recognition and detection, I think it's a really good one. And then finally, Imagenet. I think everybody knows what Imagenet is. It has about 1,000 classes with 1,000 images per classes, right? So we used all of these to train, and as you will see, right, there are multiple models that we used, and the results that we got was kind of like a combination of using all these data sets. But as far as the domain is concerned, we had eyelids and Caviar. That was our primary data set from a surveillance standpoint. So the CNN architecture, right? So Inception V3, it's one of the, I guess, if any, people who work with image processing and transfer learning and things like that, Inception V3 was one of the seminal architectures, a few years back. Now they've come up with V4, and there's ResNet and all that good stuff. But we used V3 because of it has 48 layers. It was less complex, and computationally, the number of iterations we wanted to run, it fit our needs. We use Inception V3 mostly for transfer learning. We looked into ResNet, which is a 101 layered CNN architecture. ResNet actually won the last year's ISL VRC, Imagenet Large Scale Visual Image Recognition Challenge. It had a top 5% error rate of 3.62%, and the human, they say, is about 5.4%. So it's interesting. And one of the other things was I was asking, how do you really measure a human accuracy rate, right? I mean, yes, I understand you have labeled data, so you can do computer accuracy, but how do you measure humans? So apparently there is this one person who sits through and classifies the image manually, and they compare that one person to the computer. And guess who that one person is? Thank you. Andrew Kapati. Yeah, he literally sat for a week and classified all these images. Not 1 million images, just a subsample of that.
Then the accuracy cannot be comparable.
Well, so I guess that's true, but I think what they have to compare it to human, because I think at the end of the day, what we're trying to do is we're trying to get better than human, right? Accuracy at some point. But you're right. I mean, yeah, he has to sit and manually do 1 million images if you really want to compare. But I think he took a subsample of, I don't know, thousands of images, and then that was compared again. And then there is darknet. How many of you have heard of darknet? Or it's actually nice. It's actually a pretty interesting architecture. If you see one of the contrasting things in this particular slide, the two architectures towards your left are pretty deep neural networks, right? They're pretty deep architectures. The one in your right is only 19 layers. Now, one of the things that's recently happened in the industry is that, as you can see, right, as we have come up with newer and more accurate models, like the model that just won last year on ResNet with 3.5% of top 5% accuracy, it's 152 layers, right? As compared to VGG or something like that, which was just 19 layers a couple of years back. So there's been a general, I guess, push in the industry, in the field, that the deeper you go, the more accurate classification and more accurate recognition you have. But darknet kind of is an interesting candidate here, and the reason we picked that candidate is because in cases of surveillance, right? Yes, accuracy is important, but speed is equally important, right? Because if you have an abandoned luggage and you cannot detect it in time, or you miss the window of the person and the luggage, and you can't do the association, I think you lose the whole point, because now yes, you can raise an alert, but you don't know who it is, or you can't raise an alert in time. So for us, speed was important. It was very, very, very important. So that's why we looked at architectures that were shallow but accurate. And the results later on will try to highlight what we got out of that decision. So here are some of the experiments, right? So we looked at three. So based on those three architectures, we looked at three approaches. The first approach was basically detecting an object of interest and a person of interest using faster RCNNs. So RCNNs, right? Anybody worked on RCNNs? Cool. So RCNNs are region-based CNNs. So essentially the whole job of an RCNN is, along with the classification, also propose a region. So, okay, I can tell you this image belongs to a class of cats or a class of animals or something like that, but can you tell me where the cat is, right? How do you, so RCNNs got popularized a couple of years back, and then the original RCNN was pretty lame. It was taking the entire image and it was doing convolutions over each window and then passing each window again through a region proposal network, so which was extremely slow. They came up with some more enhancement with the fast and faster RCNNs. With the faster RCNNs, what you do is you pass in the convolutional nature of basically the information of the image to each region proposal, and then you basically find out, okay, in single pass, instead of going back and forth between the images, in a single pass you can find out which region is of importance. But still, what it doesn't do for you, it tells you, okay, this region is important, but it doesn't give you the bounding boxes. It just tells you that there is that convolution window has something that looks like a cat. Now you need to take that convolution window, pass it again through the original network to find out if it was a cat. So it's kind of like, in a way, very, very inefficient, right? But it's very accurate, because doing that, now you predict a region and then you pass it again through the network, exactly that I have a double validation of my network. So that the accuracy is pretty high there. So we use that because one of the things we wanted to do was have higher accuracy along with our speed. And this is kind of how it works, right? So essentially you have an image, you pass it through a CNN. The CNN basically divides the image into multiple, in this case 7x7 grids, but multiple grids, and each grid is essentially a region of that image. Now I just pass back to the classifier and then again predict it on the class. And then finally, after you do that, you pass it to an FC layer, and that does the scoring and the classification. There's actually a really good paper here on faster RCNNs, and I think faster RCNNs are still state-of-the-art way of detecting object proposals. I think if anybody is interested, they should look at this paper. It's really, really good. All right. So the second thing was, and this is the interesting part. The second thing was darknet, or YOLO v2. So YOLO v2 has been recently very popularized in a lot of video recognition systems. And anybody heard of YOLO v2? Yeah, cool. So yes, so it's only a 19-layer architecture, but the interesting part about YOLO is, as in contrast to the faster RCNNs, is YOLO just does a single pass. So instead of going through the convolution layer, bringing up convolution windows and passing it back to the network to predict what class it is, it does one single pass and does some probabilistic identification of regions based on, it's actually uses, it also, one of the things it uses is it uses COCO as its data set. So when it has the annotation data set that it's learned from, it uses that data set to figure out, okay, is this a dog, is this a bicycle? But it does it in one pass. So when it's doing the convolution, along with the convolution, it'll also use that predicted region to, with the object annotation data set and figure out, which class it is, which makes it really fast, but it also makes it error prone. Right? Because now you're not reaffirming the convolution by passing it again through the classifier, but you're actually saying this is what I think is the region that you may be interested in, and this is what its class is based on what I think, right? So the accuracy does drop there, but I guess it's important if you use it in the right context. There are ways to get over that. So it's a pretty interesting. So for anybody who's interested in doing like real-time object detection, like if you're driving a car and you want to know if a pedestrian is on the right side of the road, if there's a stop sign, this is really good because it can give you very high frame rate based, and you can run it on a single GPU, and it's really good. Again, there's a paper here that talks about it, and it's this is basically was released last year, 2016 December. So there's some good work that's put in here. And then finally, transfer learning, right? So we didn't want to discount the transfer learning because transfer learning has provided some very significant benefits. Essentially, what transfer learning is, you take a pre-trained neural network, kind of like a Imagenet trained neural network, and you use the weights of that neural network to retrain, your own data set, right? That's important because what happens is when you pre-train a network on, like say for example, Imagenet is pre-trained on 1,000 classes, right? You gather some high-level features, some low-level features that you can, mostly low-level features that you can reuse in your own data set, right? And those weights are important. So transfer learning is actually very widely used in the industry. So let's look at some of the results, and we'll come back to transfer learning and how and what results we got through transfer learning. But let's look at some of the results we got with the region proposal network. So this is FastRA RCNN. So as you can see, this image is a little blurred, but it does a good job of detecting the person of interest here, but it completely missed the object of interest. Although the accuracy of this was high, it's comparatively supposed to be higher. The reason it missed was because the data set that we were training on, and the one Imagenet is trained on, because we use Imagenet to and COCO to do this, was not matching. So we could not actually get it to recognize our object of interest. But on a whole, FastRA RCNN does better. So we trained it on MS COCO again on the ResNet 101 architecture. Training for 1 million iteration. Training took about, I think, 7 or 8 days on a Titan X GPU. I would not recommend this training it on a CPU. And it was quite accurate in detecting people, but completely missed packages in some scenarios. So on an average, the accuracy was about 65% on our data set, right? So not bad, but a little better than flipping a coin. This actually provided us better results. So we used YOLO as a second test, and the darknet architecture, like I was talking about, was first of all, it gave us like huge speed improvements. Like with FastRA RCNNs, we were running at a frame rate of 3 or 4 per second, with one GPU. But with this, we could get to at least 20 frames per second. So we could actually do a lot more real-time computations. Again, because it's just a single pass-through for detecting both, the object as well as the region, it actually gives you coordinates of, in case of FastRA RCNN, what you get is okay, this is the convolution window that I think the image you are interested in, the object you're interested in. Now you go figure out the coordinates. This actually gives you the XY coordinates, so that's pretty cool. Yeah, and then like I was saying, if you run it on a Titan X, which is a pretty decent GPU, you get about 40 to 90 frames per second, and it performed pretty good on a dataset. So we ended up with an accuracy of close to 75%. And then finally, transfer learning. So this is something we focused a lot on as well. And essentially, remember I said in the start that the biggest problem with this domain was the lack of data sets, and not having that amount of data, you really can't train a CNN to do what it's really good at doing, right? So what we ended up doing is we ended up actually augmenting our data set, our own data set. So the base data set came with something like 4,000 images, which is not that much. So what we did was we did some scale and variation. So we actually took the original image, we flipped it. Then we took the image, we grayscaled it. We took the image, we cropped it. So we did things like that. So just to fool the network into believing that it's seeing different images. Obviously, they were the same, I guess, illumination and the same scene, but they still, became, a much more, I guess, richer data set than it originally was. So I think that was one of the things we were able to so we were able to get about 65,000 video frames to train, and they were split into, half and half for the abandoned and half for the background. Some of the hyperparameters we used was we trained it for about 200,000 iterations, just standard learning rate of 0.1, decay of 16, and train it in a batch of 100, right? So just to, and this was what we found. We actually had to do a lot of cross-validation. So whenever you build these models, you do like k-fold validations. So you have like multiple hyperparameters. You run through, iteration of those. You do grid random search, and you find out, which is the best one fitting your model. So those are some of the free parameters. But doing that, it's kind of like the base architecture where we use Inception v3, and like I was saying earlier, right? I mean, if you can leverage the weights of earlier trained models, I think all you do is you drop the last layer and essentially take your new data set and rebuild the weights on that and use that to calculate the final output score. So you take your input image, multiply it with the newly calculated weights, and you get activations, which then you can classify over a softmax equation. So it performed decently well. I guess as you'll see in the next slide, we got a test, so you got to train validation and text accuracy of, in the 95, above 95.95, and ILIS did better than Caviar because, Caviar is a little bit more messy in terms of its data set, but it's harder too, right? But when we combine those data sets, so we also actually, I think somebody mentioned this earlier, but since it's such a you have different, like train stations are different from bus stations, are different from airports, right? So what happens? Can you develop a model that can be agnostic of the domain, right? Agnostic of the scenery. We tried to do that. We tried to combine two completely different sceneries, lighting, illumination, everything, and obviously the accuracy dropped, but was still not bad. And I believe some of the recent work we have done, this is at par at what the currently published work is in the domain. We also tried to train this on and this is to prove, right, the deeper the neural network, the better the quality is. In our case, it wasn't. So we tried to train it on a ResNet 101, double the network size. A, the training was slow, obviously, but B, the accuracy decreased as well. So it was not necessarily that training on a deeper neural network gave us better accuracy. And then one of the things about neural networks is, how do you know what the network is seeing, or why does the network classify a certain image in a certain way? So there are many ways to know that, but we looked at a few ways like class visualization and saliency maps. So saliency maps, essentially, if you look at saliency map, it's basically tells you what parts of the image or get activated when you pass them through a classifier. So in this case, as you can see, there is some correlation between the image on the top, which is this is a bird actually, and the lighthouse and some kind of a skier or whatever, some person. There's some light correlation, right, between the maps here. I mean, you can figure out, like, some kind of a grayscale map but you can still figure out that there is some correlation. So that's an ideal saliency, right? I mean, if you train a very clean data set like Imagenet, right, which was like, what is it, 640, 480, something like that, 800, 600 resolution, and hand curated images, and if you train your model on that image and then do visualization, this is what you will get. So what you should expect, because those images are very curated, they're very focused portfolio-like images for that set. But in our case, this is all blacked out. I don't know if you guys can see, but our saliencies are these red kind of infrared kind of thingies here, which looks a little better on the computer, but it's not ideal, right? It's not very, I guess, representative of the scene above. And why is that, right? Why is the network building these saliency maps? So one of the ways in which these saliency maps are built is you actually compute a gradient of the image over the loss of the class. So essentially, whenever you have a class core, in this case there are just two, abandon and background, you basically do a backprop on that, and you find out what parts of the image are getting activated based on that gradient function, that backpropagation. And we got very, very messy results. But the question is, maybe the network is learning the background, right? Maybe the network is learning the exact scene, right? Maybe even overfitting, right? Now, one of the questions we asked ourselves, right, is that a bad thing, right? Because if you look at a lot of these places like terminals and bus stations, the people and the objects change, but the scenery and the background doesn't change as much. So when we tried out our models with like over multiple days and over multiple variations of the objects and of the foreground, we got pretty high accuracy, right? But when we changed the background completely, there was a drop. So maybe the network is learning the background, and maybe that's a good thing, because at the end of the day, if you want to build a system that is predicting some kind of a threat situation in a particular terminal, why not build one model per place, right? You can have one model for airport, JFK airport. You can have another model for San Francisco airport. How hard is that, right? Because once you have the model, it'll learn. So we still don't know if this is still some areas of active research, but something for you guys to take back and see how we can contribute in this area. So coming back to an analysis, right? So one of the things that actually was a detractor for us is that lack of public availability, and especially the low resolution of the data sets that we were playing with was really hard for us to train these deep neural networks. The transfer learning was promising, but it was really within a closed domain, which we just discussed, that you couldn't scale it from one place to the other. The other thing was, any drastic change in the scene had a significant drop in the production. So, for example, in an airport, now you put up a new, I guess, a new kiosk or something, that ended up, interfering with the model predictions. Faster RCNN did not provide the expected performance on the data sets. I mean, our initial assumption was, let's go with faster RCNNs, the most accurate CNN classification algorithm, and they'll give us what we want, but not necessarily, because the data sets that we were dealing with did not basically fit the needs of the model. YOLO V2, on the other hand, was surprisingly good results. We could actually get up to 60 frames a second with like 4 GPUs. And that was, although the accuracy was low, but we still could find out, and then finally, we did some experiments with ensemble models. So one of the things we did, right, so we talked a lot about how to detect an object in the scene. We talked a lot about how to detect a person, but we didn't talk much about the correlation. So one of the things we did was went back to something very basic, business rules, right? What are the business rules around, identifying a threat? You identify a person, first you go for the object of interest. There's some base assumption saying that, okay, if somebody leaves a bag behind, that's a threat. So you go behind that object of interest. Now with the object of interest, you associate a person of interest, or just a person who has the closest proximity to that object. Once you have that, now you build like a profile of that person and an object in the system, and you keep that profile. Whenever you see in the scene that those profiles are getting over a threshold, so when those two objects are separating over a threshold window, say in distance maybe a meter or something, there's a high chance, a high correlation of that person being abandoning the baggage. There could be that person has is using the restroom or has told somebody to watch over the baggage, but those are some of the scenarios that come under exception cases. But in any case, every time, so we had some business rules that we are using to just figure out what how do we associate a person to an object, and those business rules basically are used to then trigger off alarms and set on some of these. So some of these did well. So with the ensemble model, what we did was we had YOLO doing the real-time prediction. We had some of the faster RCNNs doing basically classification, and then we had transfer learning doing recognition. And having an ensemble of all of the three helped us get better results. So wanted to share some. So we actually were able to compile some of these results into some real-time videos that we were using, and these videos essentially capture the nature of how this research can be taken forward and applied to maybe even real-time efforts. So let me just show you guys what we have, and it'd be good to. So as you can see, this is some of the real-time detection happening through the model. You'll see that there is in this scene there's a lot of clutter and background, and there are people walking in and out, but it still does a good job of detecting this particular artifact, which is the luggage. Now, if you watch closely, this person is now associated with the luggage. So what the system does is it builds a profile right away, and it associates that person with that luggage. So now we have a tight coupling in the system saying that this is the person object pair, and every time there is a disassociation between that pair, we trigger alerts. So right now the system is happy, it's fine, there are no alerts triggered because we see the person standing next to the luggage.
What's the blue labels? How to read?
What was that? Oh, so those are actually detecting what kind of luggage they are. So
what's the text on the blue box?
Oh, was the text on the blue? It says suitcase. Suitcase, yeah, suitcase or handbag. Now, as you can see, that person is quietly disappearing into the hallway. So that luggage is left alone, and it's still not picking it. So the system won't raise an alarm. But as soon as it sees that, now it knows there's a handbag and we have to do some normalization here, because as you can say, you had a good question. Sometimes it says suitcase, sometimes it says handbag. So we do some normalization on those labels, and also a label, a fee texture normalization. Yes, so there are some false positives that we need to fix. Yes, so it was trying to, since it looked like a steel frame with it thought it was a refrigerator. So this was one of the easy ones, and then there are.
Good question on that.
Yeah.
This was trained on COCO or on your dataset?
This was trained on our dataset. Yeah, but the way this whole thing was put together was it was a combination of three models. One was coming of YOLO, which is trained on COCO. The second model was the transfer learning model that we built to identify the scene itself, right? And then the third model was the resonant model, which identified the faster RCNN model, which identified the object. So we took signals from three models together, and then did some kind of a weighted average on those models as to which probability of which model showed high on that class. And then the final compilation was a combination of those three models on top of the business rules that we developed. But it's not all rosy and glory, right? Because now I'll pull up another video, which is the Caviar data set. And as you can see in here, the bag is actually, so this person right here is detected as a person, and he has a backpack, and he's going to drop that at some point. There you go. Okay, I missed that window. So there you go. So he's dropping, I don't know if you guys can see, but he just dropped the bag here. But the network could not detect it because of the high clutter and in that area. So here are some of the gaps with the system where we're still. This is why this is not a solved problem, and this is why we need more research happening in this space to figure out how we can identify scenes like this, because this absolutely did not work. And then finally, there's another place where this is a little bit more harder, because in this case this bag right here is hidden somewhere behind that person, and it's actually a little scale invariant, little viewpoint variant as well. So at some point this person will abandon that bag. Did he do it? Yes. And then the system will detect it. There you go. Yeah, so this person is now disappeared into the shadows, and you can still see even without even beyond the clutter, the model does a good job of identifying it. Yeah, so these are some of the, I guess, the initial results, I may say, and that's why I guess this is more of active research than anything else, and where we need to figure out how we can make this space better for. And needless to say, I think we can extend. Yes, so I think this is where we need to actively. And then let's talk about a little bit of future work, right? So I think where we can improve this model, and is we have used ensembles, but I think there are many more ways of trying these ensemble models, in various permutations. Like we haven't looked at some cutting edge work that's been going on with capsule networks, with things like transfer learning and joint fine tuning. So recently, I think I believe it's Mr. Reddy or something someone who presented a good talk on CNN, and he talked about joint fine tuning. So joint fine tuning is a very interesting concept. So generally, if you look at transfer learning, right, what you do is you train the full network all over to the end of the classes. Like you train all the classes, and then you reuse the weights of those classes, of all the 1,000 classes and 1,000 images per class in Imagenet. Selective joint fine tuning is very interesting. What you do there is you only train a network on the classes that closely resemble your data set of interest. So in this case, right, I mean, if Imagenet has say 30 or 40 or 100 classes of things that look like a bag, right? Or things that are similar to a bag, I only train it on those, and then use the lower level representations of those features to then retrain the final layer on my data set. So there is some very promising work there, which we can leverage, and I think we can improve the transfer learning model and get to a better accuracy. Capsule networks, on the other hand, is also very interesting. So this was, I think somebody mentioned it. This was a recent publication by Jeffrey Hinton, where he talks about how when you max pool, right? So part of the convolution network layer, you have a convolution layer, you do some activations, and then there's a pool layer. And pool layer is important. The reason you do that is that your gradients don't explode, right? Pooling actually compresses your input image into smaller subsamples. Having pooling that layer, loses information, obviously, because you're summarizing that image. So there has been some, I guess, recent work on how you can actually not use max pool, but use some other advanced techniques to represent that and still have a computational efficiency. So experimenting with that may pick up the bag that was left behind in the video that we just saw. because maybe somewhere during the convolution, maybe somewhere during the subsampling, we lost information on that particular object. So there's still some work there. And then eventually, I think one thing that we did not touch upon in this presentation was use of LSTMs, because if you think about it, right, this is sequential data, right? This is time series information, obviously images, videos, but over time series, right? And LSTMs are really good candidates for evaluating sequential information, right? So can we use some spatiotemporal aspect of this particular data set, right, and apply LSTMs on top of it to figure out predictions, right? Right now we are saying this person has abandoned the luggage. Can we say this person can abandon the luggage in the future based on some kind of some correlations that we can make? So there are ways to do that. There are also ways to do actually scene graphs, which is essentially you have this image that the network see. Can it build a graph of how people in that image are interacting with each other, how objects are interacting with people? So these are extremely powerful, I guess, concepts. Obviously, they're not readily applicable to this domain, but I think if there is a lot of potential to go there. So finally, I'll end with this. There are some references that you guys can look at. Faster CNN, obviously, it's still cutting edge. YOLO 9000 we talked about. If you are ever looking how to do visualizations of image and figuring out what the network is seeing, this is a very good paper, the Deep Insight Convolutional Networks, and this is actually the paper that we published that led to this talk and some more research. And then the last one is the fine-tuning one that we just talked about. There is also actually one thing I did not put was my GitHub. If you want to pick up some code and use it for just visualizing your classifications, there are some code that we have done. I put it on the GitHub, so I'll share that. And obviously TensorFlow has some really good training material for those who want to get started with image recognition. So I'll end with that, and I guess this is really a very exciting field. I think we need more research in this area, and if I work for a company called Isera, and basically we are doing a lot of deep learning, natural language processing, and image processing there. So if you guys are looking to work in the deep learning space, the machine learning space, please come talk to me or email at this alias, and we would love to talk to you. I think that's pretty much the end of the presentation. Thanks. Yeah. Yeah.
Thank you, Utkarsh. We have a few questions that need to be answered. Number one, how do you define the baggage to detect? Abandoned baggages may vary widely in shape, texture, color, size due to the diversity and deformability.
Exactly the question. Thank you. I think that's a brilliant question, and that's the question we started with. I mean, how do you define a baggage to detect? It's so subjective, right? So I think whenever we're trying to solve a problem like that, we go back to intuition, to human experiences, to the way humans try to do things, right? How do you define a baggage, right? I mean, how do you define something? You define something through experiences, right? You define something through things that you've seen in the past, and then things that you can derive from what you've seen in the past. So that's essentially how CNNs do it as well. For us, baggage had to be defined in some way, and that definition came from our data sets, right? From the Imagenet data set, from the COCO data set, from the data sets we collected, eyelids and caviar. So that was our definition of baggages. So anything that was a learned representation, and that's why I think CNNs are representation learning versus memorization, because with representation learning you actually learn the features of an object versus the actual the syntactic dimensions of an object, right? So that's how we define a baggage, and exactly right, different shape, different texture, different color, and that's where your training comes into play, and that's actually the challenge as well, as to how do you scale that to what the network hasn't seen before. Good. good question.
We have another question. Have you considered compensating for camera angle to see if you get better results? I'm not sure if this requires more context.
Yeah, I actually, maybe I can try to answer it with an assumption.
Sure.
Now you want to generalize and call it as perspective.
Would you like to add on to it?
Perspective.
Let me get your mic.
I can just walk over.
So essentially, in the scenario where it didn't work out well, you had the guy who was almost like walking horizontally across the screen versus most other training data sets, you have people vertical, right? So clearly the way you took the camera, the image, the way it captured in the camera is kind of off. So clearly when you train a model where everything is like vertical, then now suddenly people have the capacity to essentially walk sideways sort of, right? Kind of confuses things out, I think.
Exactly right. And I think our attempt to compensating for camera angle was the data augmentation part of things, where we skewed the input data. So we flipped it, we rotated it, we colorized it. So one thing when we try to think about where these cameras would be situated across the hall is if it's behind me versus in front of me, there's a completely different perspective, right? So from an input data set, I can't do a behind and front, but from an input data set standpoint, I can do a right and left perspective. So we could, flip right, flip left. So I guess our compensation for camera angle was the data augmentation that we did. But it's really hard, because there are some positions you can never get, right? And then you have to infer. And that's where I guess that's where the training from the other data sets comes in. So like for example, Imagenet would have a feature representation of a person from the back, right? So now can I apply that feature representation to what I'm identifying in my scene, and can there be some correlation there? So to answer the question, apart from augmentation, we are basically depending on the weights that we've learned from existing pre-trained models. Yeah.
Sure, please go ahead.
Right, the question. Do you have any guess for why faster RCNN did not do as well in your case?
Yes. I think if you look at fast RCNNs, right? Fast RCNNs is primarily trained on the Imagenet dataset, right? And most image recognition models that transfer learning, right? So whichever are mostly on Imagenet, because Imagenet is kind of like the authority of images, right? Now, what our hypothesis is that since what we've been using, the datasets we've been using, right? And if you look at Imagenet's dataset, it's very profile-like pictures. So they are like very clear representations of the objects that they are trying to detect. For us, our profiles were really low. The resolution was low, the angle, the camera viewpoint was low. So one of the reasons faster RCNNs didn't do too well was because of the fact that the data we trained on versus the data we are trying to measure, evaluate on, test on was different, right?
So you didn't.
No, we did not train. Yeah, we did not train the fast RCNN network.
Oh,
but
you did with the YOLO.
That's right.
So
That's right. Yeah, and also fast RCNN training is really slow. So the other thing was that if you want to train 1 million images on fast RCNN, you probably need to have like a couple of GPUs running for at least a couple of weeks. So that's something that we want to do at some point, but since YOLO gave us a better trade-off of quality and accuracy, it was good enough for moving forward.
So I think that means your conclusions should be a little bit more specific in saying that the comparison was between a default faster RCNN and a trained YOLO as opposed to.
Well, not necessarily default, right? Because it was a pre-trained fast RCNN retrained on the final layers of the network. So the weights still come from your original data set. So just like transfer learning, right? The weights still come from your original data set, but the last layer was retrained. Yeah, and what we believe is the retraining of the last layer was not representative of what the weights in the model, existed. So that's where the network got confused, I guess. Yeah, good question.
You said you have a question?
for the eyelid dataset, how many places does the eyelid set provide?
How many what? Sorry?
How many places?
How many
I have
places?
experience with eyelid set and in competition.
Okay.
Because you are using YOLO.
Yeah.
And it's likely to, for your network to train, give the places together.
Right.
Yeah.
So
when you split your data for training and test, have you ever tried to split your data by places? For example,
that's good. That's actually a good point. So let me try to answer it in two parts, right? So it just provides one place, the eyelids data set. So that was one of the problems. But yeah, I mean, I think that's a very good. We haven't thought about that aspect of splitting the data set because ideally when you do training, it's like 80-20%, and then train test validation split, right? But that's an interesting theory. But yeah, I mean, eyelids just provides you one place, so it was not really a way to do that. Yeah.
Okay, thank you.
Yeah.
Sure, then use the mic.
Okay, so I've got a question regarding the scene graphs, as you mentioned. So those data is like Clever or Visual Genome that right now is starting to use those as part of the training, right? So you're somehow moving also into relations between objects with your business rules, as you call them. So do you have any idea how to learn those type of relations?
Within the domain, you mean? Or oh yeah. So what we're doing, one of the things that that's a good point. One of the things that we're doing is we're not necessarily building scene graph, but we're building object associations, if you may. And in our case, the objects are just pretty static. They're just people and luggage. But one of the other things that we have thought of experimenting, and we haven't done this yet, is how do you associate the object and the luggage with some kind of a time domain, right? Or some kind of relation, exactly. So yeah, I mean, that's something that we haven't looked at, but the way we wanted to look at scene graphs was that if you can so because you could do predictive analysis if you have more information over the scene. Right now we are very, I guess, two-dimensional, if you may. Just look at an object, look at a bag, and you find an association. But if you have more dimensions to measure the scene, you can derive more insights out of that. Yeah.
Okay.
Yeah.
Do we have more questions? Thank you. Thank you all for coming. Thank you, George.
Thank you.